So, in the last module we discussed a problem with integral method on how one can deal with unheated starting length, and the situation now is that we will try to use the unheated starting length, and then you can use the linearity of energy equation to obtain solution for any arbitrarily varying temperature. We will not spend, that is typically called Duhamel's theorem, and we will not take that up as part of this course. However, it is well recorded in books like Case and Crawford and so on, but we will not go into it, but it is just the idea is that because it is linear, we can take the piecewise solutions, add them up as superposition is feasible with linearity of the partial differential equation. So, we add them up and we get the solution. So, what we will see is that these concepts, even though it seems so far away from the initial discussion in the introduction part, this concept is far away from what is reality. How can we make use of this? We will see how, and as we move forward. Let us get a look at, you have a situation where there are two plates, parallel plates in this case, for example, as the simplest form. Two parallel plates are there and heat flux is entering from bottom side, while the top side has another different heat flux. This could be a PCB, top one could be a PCB, and the bottom one can be another PCB as an example. How do I define heat transfer coefficient in this case? The typical solution, if I assume fully developed flow for my velocity and thermally fully developed flow, then I can sort of get a solution that okay, this is recorded for fully developed flow thermally and hydrodynamically. The solution is that if the heat flux is equal on the top and bottom, you get an average of 8.235 average Nusselt number, which is, so this average Nusselt number based on the hydraulic diameter or the height of this system, which is h times h divided by k of the fluid. This is what it is, and this h is the average h Nusselt number or the average heat transfer coefficient. So, what happens now if I make the situation different? I make the top wall 0, the flux is 0, that is now I have only one PCB, like a video card type situation. I have one PCB, but the top cover is not dissipating any heat, and for all practical purposes we will treat that as flux is equal to 0 or adiabatic. So, what will happen to this average Nusselt number? Will it be half of this? So, if you go derive the solution, it is not exactly half, it is actually a little more than the half of this Nusselt number. So, why is that? Is because of the convective heat transfer that happens, and the boundary layer growth is going to be very different in this case. So, the boundary layer, thermal boundary layer will grow and it will actually come make contact with the top wall. Indeed, one has to account if this top wall is conducting, the wall will get heated by this thermal boundary layer as heat is picked up by the flowing medium. So, this is the solution one encounters, but now these are two separate solutions. Can we have one equation that captures all the possible scenario? And this is one example of that, is 140 divided by 26 minus 9 Q2 by Q1. So, this expression captures the gamut of situations one can encounter, Q2 being different from Q1 and Q2 equal to Q1 and so on. But there is a singularity associated with the solution when you have a situation where 26 divided by 9 is the case. So, but we will ignore those cases and just focus on this part, is that this expression now captures the variety of fluxes that is feasible, and realizing that even there is even though you say heat flux is happening from one side and the other is adiabatic, you can't make use of this expression. One has to develop the expression for the situation where flux is different from the top, the adiabatic situation is on the top, wall is on the top, and the flux is being dissipated from the bottom. So, you will not get half. So, moving on. Now, what about these cases? How will I come up with a length scale? Now, I have a heat source. This is very similar to the problem that we just discussed. I have a heat source and the top wall you can assume to be adiabatic. And bottom wall is dissipating a certain heat flux, uniform heat flux. And if I say the flow is not going to be fully developed, so what can I do? This also can be treated with simple constants, and this is I am going to use this expression to obtain the constant temperature if the wall is constant temperature, or constant if it is laminar, turbulent, if it is constant flux, then we have so many possible scenarios of dealing with. So, now we look at the situation where the heat source is not the entire length and it is only a short way. Now, what can I use to calculate heat transfer coefficient? Should I use this height or this height or the length of this device? So, what should be my length scale? Even if I say okay, this is how do I write the convective resistance? 1 by HA. In this case, I will write okay, this is some average temperature T wall minus T in divided by Q, the power dissipated by this fellow. What is the length scale is the question. So, if I have to calculate H, then I need to know what is my length scale, so that I can get the right heat transfer coefficient. If I use wrong length scale, I am going to get different answers and we will not know which one is right, what we are predicting is right or wrong. Now, going to even complex case is we have two heat sources, 1 and 2, and flow is happening. Now, flow is coming in at certain temperature in, this has a power of 1, this has another power level of 2, there is a T1, T max or T wall 1, T wall 2. Now, if I were to use, let us say I assume that I can use the length of my source as the length scale, this is L1 and L2. What will I use as temperature? If I want to write a resistance, I want to use T wall 1 minus T in by Q for the first source, which is okay. What is the temperature? What is the resistance for the second one? T wall 2 minus this temperature, which is mean temperature, or the inlet temperature. What will be my reference temperature for the case, or this is P1, let us say, and this is P2. So, what becomes challenging is that now as you have more heat sources, now whether this heat source, the standard definition of resistances will work for this, or this definition of reference. So, we encounter two situations, finding out what is the length scale, what is my reference temperature, that I need to use to define a resistance. Because resistance network are very powerful, because you can deal with n number of sources and connect them from a single heat source or a multiple heat source to an ambient that is single. So, these are the typical situation that we encounter, and as we can see now, there is a boundary layer, there is heat generation happening in this case. How do I define? All these situations define or are asked the same question, how to define what is Reynolds number, what is length scale, what is temperature reference. So, for that we will take a simple and quick look. Let us look at a simple situation which was simulated without much effort on computational power. This was done on a software called IcePack, and the numerical accuracy was not tried to be as best. It was done so that quick and fast solutions can be obtained. So, here is the situation. This is a PCB over which air flows, and this is a top view, and this is the side view on the bottom. This is the side view. This is the top view. As you can see, the heat source is mounted on the substrate. This is the heat source and it is not protruding out. Most of the situation warrants you to have the heat source protruding out, but in the case of voltage regulators, inductors, the FETs, the field effect transistors, the heat sources or the pads are actually on the PCB itself and they need to be cooled. So, let us assume such a situation where there is a heat source, a small pad that is inserted in the PCB and I am flowing air and the PCB is slightly conductive. So, what happens is that as air flows, there is a wake, like very similar to a flow past a cylinder, there is a wake, thermal wake that develops. And this is the flow direction, as you can see, and you will see that a thermal wake is developed and you can look at the velocity that is incoming here. It is uniform velocity here and it quickly develops into a fully developed flow, in hydrodynamically fully developed in this case. And a thermal boundary layer starts to develop, very similar to the unheated starting length we discussed. So, what is this doing to us is that the temperature, even for this case, this power level is only 0.5 watts and we are bringing in some 3 meters per second of airflow going through this channel. This is about 300 millimeters in length. So, a typical 200 millimeters in length, a typical motherboard configuration. So, what we half width motherboard. So, anyway, this is a simple scenario where we see that the PCB, there is a lot of temperature effects felt on the PCB. So, any of the components, so air is going to get heated even past the heat source because the heat is being conducted and being dissipated into this. So, the thermal boundary layer grows from this heat source, even though the heat source has ended, it continues to develop because the heat is being continuously dumped from the PCB into the airstream. And outside of this wake, there is no influence of the heat source. So, if I were to place a component downstream, so I am going to see that the heat from this source is going to couple with this heat source and also through the substrate and also through the air medium. So, now the dilemma, what is the heat transfer coefficient? So, there are many possibilities as we discussed. One is to talk about fluid inlet temperature, let us say this is some T naught that is entering or T inlet, and you can use T naught as a reference temperature and define a heat transfer coefficient. So, what is my heat transfer coefficient? Heat flux divided by T wall, which is at least fixed, minus T in, is the situation that describes in this first slide. Or I can use mixed mean, which is the bulk mean average temperature of any fluid that is passing through internal flow through a medium. We typically use this, but look at this situation and we will discuss this. And the other one is the log mean temperature difference that is often used in heat exchanger design and so on, or what I am going to call as a adiabatic temperature. We will hold the discussion for a little later, but we will discuss these two guys first. And you can see that there is an inlet temperature comes in. So, I can define my heat transfer coefficient as power of the heat source divided by the area. This is my flux, and wall temperature of that particular heat source, let us say Tw comma I is for 1, and T inlet, this is my, because this is a common reference, so it becomes easy to use because that is a known temperature, because we will not know what is the temperature over here or we have to do something else, and we will discuss. So, this is one definition of inlet based heat transfer coefficient. Then we go to the next definition, which is based on bulk mean temperature. So, we use m. How do I get bulk mean temperature? Q equal to m dot Cp time temperature difference. If I know my inlet temperature, I can find what is my mean temperature of the heat source 1 equal to Q divided by m dot plus T inlet. What is the underlying assumption? If we refer to the meaning of bulk mean temperature, the assumption we make is that the fluid is well mixed in this area. The fluid is well mixed. if the proximity of this heat source and this heat source are close, then there is no time or the space enough to have the fluid temperature mix well and have a uniform temperature. That is the meaning of a bulk mean temperature, is to have the fluid somehow you pull out magically at a plane, you pull out the fluid, you mix it and you measure its temperature. That is the definition of mean temperature. So this is the temperature. So you can similarly define something based on LMTD as well, and so on. So what is the real situation that happens? Is that now you have a situation where if I look at the temperature profile coming out of this is my mean temperature profile, but look at the temperature gradient at this point, it is going to look something like this. That is, the temperature profile will be hotter at the bottom and uniform at the top. So this will be T inlet. So here it is going to be T inlet, because my boundary layer has grown only till this point, anything above this is going to be flat. T inlet temperature, and it starts to be higher as we go, and as it is in contact with this hot wall. So you have a temperature profile that is different throughout the height of the duct. So if this distance S is small, this is small is a vague term, we won't be able to quantify it. The idea of small here is that it is not sufficient for this hot fluid and the cold fluid on the top to get mixed and give us a mean temperature like this, which is a flat line. Then this hot temperature, that is essentially this fellow, is going to, the same hot temperature is going to make contact with this inlet. So you are going to encounter a situation where this hot temperature becomes the inlet to the next heat source. So this is the situation we encounter in electronics typically, and how can we define a heat transfer even with LMTD? So mean temperature has no meaning because there is a large gradient in the profile, and mean temperature means well mixed temperature. So what do we do is what is called the adiabatic heat transfer coefficient. First, what we do is that in a situation like this, we have power source 1, power source 2, we turn off the power source 2, we turn this fellow off and experiment. This can be easily achieved numerically, but we will just for now see that some method is there, experiment or numerically. We power off this device and get the temperature of the device with only this heat source powered on. With this heat source powered on, we find the temperature of this. Then that temperature, this is the wall temperature, power temperature of this heat source. This wall temperature at which when the power was turned off is called the adiabatic temperature. This is the effective temperature of the solid, because this temperature, that the preheated air will make contact with this solid. So that will heat up this solid. So that temperature becomes the actual temperature of the reference temperature or the reference temperature. So this reference temperature, we should treat it as adiabatic temperature. So this adiabatic temperature is not a fluid temperature, it is actually based on the wall temperature, and we can show that it is an invariable descriptor in terms of heat transfer coefficient. If we use that as a way to measure heat transfer coefficient, which we will call as adiabatic heat transfer coefficient, as T wall minus T adiabatic. This heat transfer coefficient will be called as adiabatic heat transfer coefficient if we use adiabatic temperature. And this is the use that we can make use of the surface temperature, arbitrarily varying surface temperature profile, because easily we can say that at that point you can turn off the power and measure the temperature at that point, and make use of the same profile, and so analytical solutions are feasible, or at least a framework using the unheated starting length becomes very feasible if you allow for unheated starting length or arbitrarily varying temperature distribution, because we are playing with the idea of heat source turning off, turning on, and that can be easily achieved with a simple code. So, moving forward, so if we had another heat source on the, no problem, you turn that off, see the temperature, adiabatic temperature of this by turning that off, and go on measuring similarly and measuring a heat transfer coefficient. What is this going to do? So, let us look at this example where one heat source, protruding heat source, is kept and heat flow is happening. There is conjugate heat transfer happening through the conduction on the bottom. So, you see that there is a recirculation zone because there is airflow is happening, fully uniform flow comes in, becomes fully developed, but because of the object is there, there is a separation that happens here, and the flow gets squeezed between the heat source and the top cover, and then comes back, and then there is a recirculation zone, and it redevelops into a fully developed flow when it exits the system. However, the thermal boundary layer grows very significantly, not from just the even before the heat source there is a thermal boundary layer because of the conduction through the substrate, and this we call as the conjugate heat transfer. For this discussion, we will stop with this discussion saying that conjugate heat transfer is a very important aspect, but we will not be able to carry forward. So, we will keep this and situation, and now look at the situation where we have two protruding heat sources. Here is the heat source 1, heat source 2, this is the temperature boundary layer that is developing, and you see that the boundary layer is developing and the velocities are, and you see that the maximum temperature that is achieved in the second heat source, as you could expect that the temperature profile from the hot surface is making contact with the next surface. So, even though the mean temperature is only 20 degrees, the inlet temperature is 20 degrees, mean temperature is only 20.5 here, but the actual temperature here is the blue regime, which is closer to 25 to 27 degrees Celsius. So, that 25 degree is making contact with the next heat source. So, the next heat source is much hotter in comparison to the first heat source, much hotter, because this is in the yellow, which is in the 41, 42 degrees, and this is 48, while the mean temperature, this is inlet at 20 degrees Celsius, and the exit after the heat source, the mean temperature is 20.5 degrees. So, if you look at it and we go and calculate an adiabatic temperature, which is turn off the power of the second heat source and let the power only the first heat source, and we measure the temperature using the conjugate effects and everything, you see that you are getting a temperature that is 24.6. This is what is called adiabatic temperature. This powered off the temperature of the source if it were powered off and only influenced by the heat sources present elsewhere. In this case, we are talking about one heat source, but you can have a 3-dimensional array of heat sources and can still measure the adiabatic temperature for those things. It is a simple matter of running different simulations in the situation. So, then you can calculate, as I mentioned previously, the mean temperature at this point is only 20.5 degrees Celsius, while the incoming temperature is 20 degrees Celsius. So, now use this temperature and we will go ahead and calculate the heat transfer coefficient. The heat transfer coefficient for based on mean temperature says that for the first heat transfer coefficient for the first source is 56.5, second source is for 44.9. This is based on mean temperature. If you use inlet temperature, you will get very drastic results, but anyway we will use mean temperature. So, which says that heat transfer coefficient is changing from location to location based on where it is presented, what temperature it is seeing. So, it is, which is not the nature that we expect from a heat transfer coefficient. We want the heat transfer coefficient to be same anywhere. It should be an invariant descriptor. Heat transfer coefficient should be same whether it is higher temperature or lower temperature, whatever it is. So, in this case, if I use adiabatic temperature with very less accuracy simulations or grids, you see that they are very close. So, you get the heat transfer coefficient is 56.5 watts per meter square Kelvin and 54.4 watts per. So, these are very close values compared to these guys, which is very different. So, you see that adiabatic temperature, the invariable the heat transfer coefficient becomes almost constant, and that makes it very powerful way to do any 3-dimensional circuitry. And the unheated starting length problem can be adopted, and we will see how in the upcoming discussions can be adopted to achieve the invariant heat transfer coefficient, and how to map if we end up having an array of heat sources however you want, and how we go ahead and calculate, we turn off one power, use the power on, and see the influence of each of these heat source and calculate its adiabatic temperature and so on. And we can use the for a duct arbitrarily varying wall or flux conditions and get a what is called superposition kernel function, and we will just very briefly discuss that in the upcoming discussion.